So I'm going to start by sharing my screen and quickly run through what we did in the last class. We looked at the representation of an arbitrary shaped curve, in a parametric form, and we looked at a particular form, which is a parametric cubic form, where we saw that the algebraic form, which is here. Let me just highlight it somewhere over here. This is the algebraic form, and we decided that while it is good for computations and as an internal representation for defining the entity, we cannot expect people to input algebraic coefficients. We would rather have to give, oops, sorry. I hope I can fix this problem by pressing this. Yeah, no, it doesn't. One second. Okay, and I'm just going to unplug and plug again. That's the easiest, I think. That didn't help either. Okay, so just bear with me till I sort this out. Yeah, it looks like sorted out. So we came up with a set of geometric coefficients, which are the two endpoints and the two tangents. The picture is up there. And it turns out that we can't prescribe tangents or derivatives either. We can only prescribe slopes. And therefore, you get an additional degree of freedom. And we saw that allows us to, get slightly different shapes and with strange inflections and things like that, right? So that's the picture that we had drawn here. Because the slope leaves the magnitude free, you have an additional degree of freedom to sort of do this. So what we have at the end of this is a representation which can be defined intuitively in a geometric sense by the user, right? And it allows any number of arbitrary shapes for which we may not know the equation, but at the end of this, you will end up knowing there because you are prescribing B. You know the representation of the curve is this matrix here as written in this expression. And from this, we can also get the algebraic coefficients because A then is equal to MB. Right? So the only thing that the user changes here is B, M remains a constant, and you can get as many shapes, arbitrary shapes that one would want. So first is any questions so far? Any questions?
Sir, hello, sir.
Yeah.
Sir, this is Shankar here.
Yeah.
Sir, actually, this is my first class today I'm joining. So
Okay.
can you kindly add me to the team, sir, so that I will be able to access the old recordings for this class?
Yeah, you need to send me a mail, but I'll do it after the class. Yeah.
Sure, sir. I'll send you a mail. Thank you.
Mm-hmm. Yeah. Okay, so if there are no questions, then I'm going to ask you a question. That we had the goal that we wanted a mathematical form for a curve that does not have a closed form equation. Yes. And therefore, that goal has been achieved, right? So for any conceivable shape, right, broadly speaking, you have the two endpoints defined, the end derivatives or end slopes in your mind, and you can automatically get a representation for that once you prescribe those. So in that sense, our task is done already, right? We can represent arbitrary curves. What can it not do right now? Or can we stop and go on to surfaces with this? Any questions and any answers? With the parametric cubic or the Hermite curve, can we say that, okay, we are done representing arbitrary curves, let's go on to surfaces, or are there still issues that this cannot address? Well, let me prompt you with another question. I have to shut this off. Hang on a minute. So the question that I would like to ask you is this, that, can we consider a non-cubic curve and see what happens, right? So supposing if I say for whatever reason, right, we need a fourth or a fifth order curve. So I'm going to write down the algebraic form for you again. P of u sigma I equal to 0 to 4 ai u to the power I, right? Let's say that instead of the parametric cubic, I write a parametric quartic curve. Same question again, that this is non-intuitive because it is only algebraic coefficient. We don't know, right, by what will happen to the curve when I change any of these. And alternately, given a curve, I don't know how to find the values of ai corresponding to that directly, automatically. So what would be the equivalent set of geometric coefficients here? Any thoughts? Well, first thing I hope you agree is that I need more degrees of freedom to be fixed, right? Because I have 5 coefficients now, and therefore I need 5 pieces of information. And as the degree keeps increasing, we need to prescribe more and more entities or values to fix the degrees of freedom. And that becomes more and more difficult, right? I mean, these are easy here. And even this is not so easy because remember, in 2D, you can prescribe a slope and some additional information and get away with it, right? But in 3D, it is very hard for you to prescribe the slope also, right? And as the degrees of freedom increase, you have to give more and more information to prescribe the shape, and that becomes increasingly difficult, right? So therefore, this form of the representation, the parametric form, this way, right, where I have to prescribe the coefficients directly somehow, is not going to be a good solution for us for higher degree curves. Cubic we have managed, maybe we can manage quartic, but as we go higher, it will not be a good idea. That's point one. And the second point is the one that I just made some time back, which is that it is not easy for you to define the derivatives at the end, right? This is the requirement. For 2D case or the planar case, we can escape by saying that, okay, it is easy for me to prescribe the slope, so I can prescribe the slope, and there are some additional degrees of freedom. I fix that by giving some additional information, right? But there is a lot more than just giving this additional point. Can somebody tell me what else is required? When we discuss this case of the use of a slope as opposed to the derivative, right? We said that there are 2 degrees of freedom, right? We said this that P naught of u can be written as K1, M1, K1, 0, etc. So there is an extra degree of freedom here. Likewise, here too, there's an extra degree of freedom, K2. And so we said, oh, I can fix it by prescribing a point in the middle, and I can solve for these K1 and K2, and so I get a unique curve. That is correct. That process is algebraically correct. You will get a solution. But as a user who is defining the curve, can you tell me what is the difficulty in just picking a point here? What else is missing, or do you have to give any other information? Any answers? Well, how do you solve for the unknowns? The only way you can solve for is by saying, so let's put this point as P star, right? So you are going to say that P star is equal to A naught u power 0, so that is not there, plus a1u plus a2u square plus a3u cubed. This doesn't help you, right? Because unless you get some equation in terms of a0, a1, a2, a3, you cannot use this to solve for the unknown entities, right? And the only way you can do that is by prescribing for what value of u do you want this point to lie on the curve. Remember, we had said that the curve can be seen as a mapping from the parametric space to the Cartesian space. So this point corresponds to 0, u equal to 0. This point corresponds to u equals 1. Same ways, you must also say what value of u does this point correspond to. And that's not that intuitive all the time, right? If you happen to pick a point exactly at the midpoint of the arc length, then you can say this is 0.2, 0.5. But then that also is not easy if you are given some strange shape that you are interested in. So therefore, while conceptually this is a parametric representation and you do have the ability to represent arbitrary shapes, these are two issues. One, as the degree increases, your ability to prescribe the degrees of freedom in an intuitive manner goes down. And two, even for the cubic case, it's not that easy for you to prescribe the information that is required in space. In a plane, possible, but in space, not so easy. So that then demands that we come up with a solution to this problem, and that is what we are going to do next and talk about the solution to this, which is the Bezier curve. Let me just hide this so that I can get some space to work, right? Now, the Bezier curve actually bears the name of the person who came up with this representation scheme, right? And the motivation behind his development, it's Pierre Bezier, was the following, that instead of having the user to prescribe entities that are there on the curve, right? So I need a point on the curve, endpoints are okay, but this point is difficult. We have seen that. Instead of this, the idea was that the user or the designer is able to sort of nudge the computer to find the right shape of the curve. So if you see these 4 points that I have marked here, right? The question I ask you is that what kind of a shape does this imply to you in your mind? Clearly, these 4 points do not, imply a shape like that, nor does it imply a shape like this. The more logical thing would be a shape like that, right? That's the intuition behind this whole Bezier curve, that the user, in some sense, nudges the computer to the shape that he or she is interested in by picking these points. Likewise, if the user pulls this point upwards there, one would expect that the shape that he or she is interested in looks like that, right? That's the idea or the motivation behind the Bezier representation, that allow the user to define the shape of the curve through points which are not necessarily on the curve, right? But rather guide the shape of the curve. And this is also very well suited for a person sitting in front of this computer screen and moving these points around till he or she is satisfied with the shape that they are interested in. So that's why we call it ab initio design. Clean slate, you start off, pick these 4 points, you get a shape, move this up, you like this, move this down, sort of like that, and so forth. And you can keep shaping and stop when you are happy with it. So that's the intuition behind Bezier curve. Now, a quick about the actual representation itself, the algebra of the curve. So if you see the form of the curve, it looks very similar to what we saw the geometric form of the parametric cube in the last class, right? So P of u in the last class, we saw it as Fi Bi, and I'm sorry about the notation here, but that's okay. So this is I equal to 0 to n. And we said that the Bi's are the user input, right? The 2 endpoints and the 2 tangents or the derivatives, right? And the Fi's were basically polynomial functions in U. right? That's what we had in the last class. If you look at the form here, right? Again, you have two entities, pi and bi comma n of u. Clearly, this is taking the role of fi because this is the function of u. Now, what function we will just show you in a minute, but rest assured it will be a polynomial function. And pi's now are the user inputs, and these are called control points. And because your index is running from 0 to n, there are n plus 1 points, control points. So in this example instance, I had, before I moved it, I had 1, 2, 3, and 4 points, right? And therefore, this is a cubic curve that I get in this formulation. Now, the form of that function, the polynomial function of u, it takes this form, which is written here. NCI is a combination which expands to, for those of you who want this corresponds to n factorial by I factorial into n minus I factorial, right? And u power I, 1 minus u power n minus I. That's the expression. Okay. Now, this whole expression comes from high school algebra, right? Those of you who remember this thing, it's called the binomial expansion. Okay, so some of you might still remember this, the binomial theorem and the expansion, and these are the coefficients of the binomial expansion, right? And that's the but for these purposes, these are known as the Bernstein polynomial. That's just the name. Okay. So some quick observations, and before we start talking about properties and more details of this, right? If I were to evaluate this for 3 points, which means n is equal to 2, then I get an expression that looks like this. Okay, I have just expanded, substituted for bi comma n with this polynomial, and I do the math, and I get this expression here. It's a quadratic polynomial, therefore the degree is 2. And so that's the first conclusion, that the degree of the curve is always n, and the order is n plus 1. So the control points, the number of control points that you input will decide the order, and the degree will be 1 less than that. That's point 1. Okay. The second point is, again, by just plugging in, I'm going to write down the expression for the cubic case just so that you feel comfortable with that. There's a mistake here. Yeah, this square should be outside the bracket. Sorry. Okay. Okay, so that's the equivalent expression for the cubic, right? And clearly, if you can see, P at u equal to 0 is nothing but P naught, because all these 3 terms drop out. And P at u equals 1 is equal to P3, because all these 3 terms drop out. And so, even though you are prescribing 4 points that are, as I said, not necessarily on the curve, the expression that you have chosen for the curve, the representation that you have chosen for the curve, ensures that it will always interpolate the first and the last point. Always. I have shown you for the case 3. You can quickly verify it for the case 2, and we will later see a geometric argument as to why is inevitable, right? That the curve, the Bezier curve, will always interpolate the first and the last points. Okay, and you can write down an expression for the derivative of this and convince yourself that it will always take off tangential to the first polygon leg and arrive tangential to the last polygon leg. My drawing is a little bad here, but it is tangential here and here. Okay, so what we are saying now is that even though you started out by assuming, or rather considering, that you would like to provide a tool that will allow the designer to sort of nudge the shape, it turns out that the designer has much greater control over the predictability of the shape, right? Much greater predictability is there, meaning that the moment you prescribe 4 points, you can immediately, mentally at least, draw a picture of what the curve will look like. It cannot be anything but this. Okay. Now, the reason why I'm saying in a much stronger way is there are other properties of the curve in play, and we will just come to that in a minute. But the point to be kept in mind is that these are all automatic, meaning it doesn't matter what n you choose, where you choose the points. You can choose points like that. So this is my control polygon. My curve will look like that, guaranteed. Right? You can evaluate it and you will see that it has to be like this. Why? Because, as I said, the curve has to interpolate the first and the last point. The curve has to take off tangential to the first polygon leg. It has to arrive tangential to the last polygon leg. And so it gives a very great amount of predictability and intuition to the designer in terms of the location of the points and the shape he or she is interested in. Right? So that's the nice thing about the Bezier curve. Quick thing about why we call it the basis functions, right? Best way to think about this is that think of your Cartesian reference frame. Let me make some space here on the side if I can find my mouse. Yeah, here. Right. So the reason why we call it the basis function is that think of how you define a point in 3D space. Right. So you have some coordinate x in this direction, some coordinate y in that direction, and some coordinate z in the other direction, right? And so the point is prescribed as xi plus yj plus zk. Right? This is the vector that defines that point. So here I have these coefficients x, y, and z, and the basis function, which are vectors, which are these ijk. Right? So the ijk forms a reference system for me in which I can use these coefficients x, y, and z to locate a point in that space. Right? That's the idea. So these ijk are said to be basis vectors. I, j, and k are said to be basis vectors. Right? Like same manner here, right? The bi comma n of u are not 3 basis functions, but n dimensional, n plus 1 dimensional basis functions. Right? And each of them, right, just like I have I, j, and k here, I have bi comma 0, bi comma 1, all the way till bi comma n. These are my basis vectors or basis functions. Except that it changes for values of u. So let's just ignore that and assume that for a fixed value of u, these are my basis vectors at that point in time for that value of u. And if I weigh each of them with these input points that I have given, p0 to pn, then this weighted combination will give me the point on the curve. So if this is my parametric space 0 to 1, for a fixed value of u, I have these, n plus 1 basis functions. Here I have these 4 basis functions corresponding to the n I have chosen here. And I weigh them with each of these input control points, and I get a point on the curve, which is that. Okay, so that's why we call it as a basis function. The algebraic form is like that, that I have a weighted combination of these basis vectors, I get a point on the curve. Okay, so that's the introduction to the Bezier curve. But the main thing that you need to remember about, and just an example here, that I have 5 points, sorry. So this is the original set of points that we have, right? and the corresponding Bezier curve is the one shown in the solid line here. Now, for some reason, the designer chooses to move P2 to this location here, and you can immediately predict what the curve will be because you know that it still takes off tangential here and it still has to arrive tangential there, and therefore that's the shape of the curve. Okay. So as I said, there are other properties that ensure that this has to happen. So let me list you the properties that the Bezier curve has. We've already seen the first one, which is that it interpolates the first and the last control point. Right? So no matter what your set of points are, it will always go through the first and the last point. Again, curve is tangent to the first and the last segment of the control polygon. This again is true no matter what n you choose. It will always take off tangential to the first polygon leg, P0, P1. It will always arrive tangential to the last polygon leg, Pn, Pn minus 1. Okay, so that's again always true. Now the next property is the one that we need to is a new one, which is why I was very confident that in this case I told you right that the shape of the curve will always be this way. I don't know where that curve went. Somewhere I drew here, right, and here. These curves have to be like this only. They can't be anything else, right? What do I mean by they can't be anything else? You may argue that I can satisfy the condition of being tangential here and tangential here, but have a curve that looks like this, right? And likewise here also, maybe you can get some strange looking curve like that, right? But we preclude these curves and we say it is guaranteed to be this or this. And the reason for that is the third property that we have just listed below here, that the curve shall always lie within the convex hull of the control polygon. Now, I don't know how many of you have heard this term convex hull. Has anybody encountered this term before? You can say yes or no.
No, sir.
Okay. So mathematically, convex hull essentially refers to for a set of points, right? Convex hull of set of points. And I will talk about the 2D version now, but the definitions apply to a 3D version of set of points as well, right? Points in 3D space as well. So formally, it is defined as the smallest convex combination of these points. Now, what does convex mean? Convex means that if I join a line, if I join 2 points in that set by a line, right, the line stays inside that set. It doesn't go outside the set. That's what we mean by the convex combination. And the convex hull gives you the smallest convex combination of the set of points. So let me illustrate this for you. So let's say I take a bunch of points. So these are the set of points that I have, right? Given in the plane of the screen of the computer, right? So these are the points. Now, physically, one way to think about this convex hull is that if you sort of take a rubber band, think of these points having pins located at each of these points, right? All pins or drawing pins stuck to them. And you sort of stretch a rubber band, to the two extremes, right? And bring it to the plane of the board or the screen and let it go, right? So what is the shape that the rubber band will take? The shape that the rubber band will take is indicated by this shape. Okay. So that's the convex hull. So it's a convex combination of the points that have been given, but it is also the smallest possible convex combination. Right? So go back to our example. If I pick my control points to be this, what is the convex hull corresponding to that? The convex hull corresponding to that is this triangle itself. And what this property says is that no matter what happens, my curve will always stay inside this convex hull. It cannot go outside. And that's a very powerful thing, because that is what allowed me to draw this picture without actually even calculating anything, right? And I would not have been too far. Even if you were to calculate with these 4 points, I would not have been too far from the actual curve, because of these properties: endpoint interpolation and tangent, and then convexal property. And likewise, same thing here as well. So for these 4 control points, let me just change the color so it helps. So for these 4 points, which are the control points that I had taken, the control polygon is that. And that is why we are sure that the curve has to be like this. It takes off in this direction because the tangent here is like this. It has to come back in this direction because the tangent here is like this. And it cannot go outside this box, and therefore this is the only shape that it can take. So the properties of the Bezier curve turns out that are very nice properties that allow a great deal of intuition and predictability on the shape of the curve. Therefore, even if you were to choose a very, strange looking control polygon, like that, you will be able to. So let me just flesh out the control polygon for you. Right? You will be able to draw the shape of the curve without too much difficulty. Right? Why? Because you know that it has to take off here, it has to come here, and then in between, it cannot go outside this box that we have drawn, and therefore that's the shape that you can get. I'll come back to this after talking about the last one here, which is the variation diminishing property. Okay, what we mean by variation diminishing, again, there is a mathematical definition which says that if my control polygon, right, which is this input points, intersects a line, right, say 2 times, then what this property says is that the curve corresponding to these control points cannot intersect this line more than 2 times. At best, it will be 2. I mean, at worst, it will be 2, and at best, it might be much less than 2. A very simple example here. If I were to draw a straight line, to make my case, something like that, and let's say this curve, even if it intersects it twice, right? So the curve is intersecting the line at these 2 locations, but it is intersecting the polygon at 1, 2, 3, 4 points. Right? So that's what the variation diminishing property is. That even though my control polygon may have a lot of wriggles, right? My curve will tend to smoothen out these wriggles. That's what this property does. Right? Now, this is significant because at that time, remember I said that people were more used to defining curves by points that lie on the curve. And interpolation used to be the most useful and technique, right? So the only way you can interpolate all these points is to have wriggles in my curve. This one does not interpolate the points. It gives us a shape that is defined by these points, right, in an indirect way, but it tends to give you a smooth curve as a result. Okay. Let me just park this for a minute, and I will come back to this after I introduce one more part. But before I do that, again, a little bit of algebra for you, because as I said, in the previous case, we were internally, writing the curve as a polynomial of the type ai u power I. Now, this is nice because, there are a lot of solvers for the roots of equation, intersection, everything. This form is very useful, right? Computers, we can write programs, Newton-Raphson techniques, and so forth like that. Whereas if I have an expression like this, right, then I have to first expand these and then get this. But it turns out that it is easy to go from an expression like this to an expression like this by just computing these terms in this form, UMB. And once I know MB, I also know A, and therefore, the Bezier curve internally for all further manipulations can be treated as a polynomial expression. But from a definition and intuition point of view, this has these very desirable features. Okay, now remember this was proposed by Pierre Bezier, as I said, who was working for this car company, called Renault. And as I said, his vision was that there was a new CNC machine, numerical control machine, not C, only NC machine, that was obtained by this company. And his desire was that the designer sits next to it and clicks on these points, gets a shape, right? And then you download this shape onto the machine immediately, and it cuts the styrofoam into the shape, and it can be shown to the supervisors, and they approve it, and then you can cut metal. And that was the grand vision that he had. So let me just slightly change tack and go back to the same original set of points and go through some construction, right? So I have these 4 input points, right? P1, P2, P0, P1, P2, P3. And in this construction, unfortunately, I put both the steps here, but that's okay. What we do is that we take successive legs of the polygon, in this case, P0, P1. I need to move this a bit inside, sorry. Yeah, P0, P1, P1, P2, and P2, P3, and mark a point corresponding to a linear interpolant of these 2 points. See, what is the linear interpolation? Some linear interpolation of 2 points is 1 minus u P1 plus, sorry, P0 plus u P1. Okay, that's the linear interpolation. I evaluate this for a particular value of u star, and that's called the linear interpolant at a particular value. That's what I have drawn here. So assume roughly half. So 0.5 you assume. It's not exactly half, I think, but doesn't matter. Okay. So I get this point here, and I get this point here, and I get this point here. Right. Each of them can be computed according to this expression here. Now I take the 3 new points, right, and do the same thing again. Now I have 2 pairs, this, and I calculate the interpolant for, say, u equals half, and I look at this, and I find, and I get this point corresponding to u equals half. Now I again take the new set of points that I have, but now I have only 1 pair, therefore there's only 1 linear segment, and I find the interpolant corresponding to u equals 0.5 again, and that's what this is. Okay, now this is purely construction, right? I mean, I find, take points in pairs, find their interpolant, mark that, and then work with the first level of interpolants, and do the same thing. Then I get the second level of interpolants, again take them in pairs and do the same thing till I have no pairs left, as you have in this case now. There's only 1 point, so you're done. You started with 3 pairs, 2 pairs, and then 1, and then you stop. So what is the significance of this? The significance of this is here. Right? So the same thing, ignore these labels. That's, useful, but unfortunately we don't use the same labels, but you don't need them either. So you can just look at the picture, right? So first pair, second pair, and third pair, you get these 3 points, P01, P12, and P23. These 3 points have 2 pairs of lines. You do 2 more interpolants. They form 1 line. You get 1 main point. It turns out that that point lies on the Bezier curve for the value of the parameter that you had chosen. Okay. Now we can show this algebraically also. I'm not going to do that. I just want to I want to show it to you through a picture, but you can also show it algebraically. Now this means that you can generate points on a Bezier curve, right, by just doing this construction. Okay, what does that construction say? Instead of 0.5, you can do 0.25, 0.25, 0.25. And then on that line 0.25, on this line 0.25, and then on this line 0.25, and you will get the point on the curve corresponding to u equals 0.25. Right? So this becomes a very powerful way then to generate points on the Bezier curve. See, that's what you have done by doing how many linear interpolations? 3 in the first step, 2 in the second step, 1 in the last step. So 6 linear interpolations, and you get a point on the Bezier curve. And you do this for all the points, and you can keep generating all the points, and then you get your Bezier curve from that. Right? So this turns out to be a very interesting way to sort of construct the curve rather than looking at that algebraic form where you had these n factorials, etc. Right? So on the one hand, I have this n factorial by n minus u factorial by u factorial, right? I factorial, sorry. And then you have these powers here, 1 minus u to the power n minus I, u to the power I. Now, those of you who remember what these factorials are will know that 0 factorial is very awkward. Division by 0 on both sides is very awkward. All of these are, things that computers are not very good at. And your program has to sort of cover for all these extreme cases or singularity cases. Whereas here, all you need to do is do a series of interpolation. And I'm going to write it in a slightly different form by now I'm going to put these labels. Unfortunately, I don't like their labels. Okay, I'm going to scratch it and write it on this itself. And right. So I'm going to call this as P01, P11, P21. And this point here, I'm going to call this as P02, P12. And the last point is P03. Okay. And I'll rewrite this in the new notation that I have written, which will be Pj of R equals 1 minus u times Pj of R minus 1 plus u into Pj plus 1 of R minus 1. Okay. So R in this case goes from 1 to 3, right? So this is 1 to n. N is 3, right? 4 points. And j in each case goes from where, right? In the first case, it goes from 0 to, where is the last one? P2, right? N minus R. So either you evaluate the curve using an expression that has all these terms, or you implement this simple for loop and you can generate points on the curve. So this becomes a much nicer way to do these things because you're only doing linear interpolation, exact calculation, nothing, no singularities to worry about, and therefore you can construct the curve very rapidly. So this algorithm is known as the de Castelao algorithm. And as it turns out that he was about 3 years before Bezier, he had developed this algorithm. But as luck would have it, he didn't publish this article or publish this technique, and therefore the name on the curve went to Pierre Bezier. Okay. But to be fair to Bezier, I mean, once he discovered or when he came to know and saw the original notes of de Castelao, he was the first to acknowledge that it is de Castelao's scheme. But nevertheless, Bezier's name stays on the curve. Okay. So that's an interesting aside that you may want to remember if you end up taking an academic or a research career, the importance of claiming your work through a publication, is important. Okay. Now, the reason why we say we study this at all, A, of course, it's for your own interest because this is a more construction-based technique and therefore intuitive and much easier for you to construct the Bezier curve instead of remembering that expression or the formula that we had seen for the Bernstein polynomial. But the more interesting thing is that this also tells you why some of the properties of the Bezier curve accrue to the curve, right? Because we are doing a series of linear interpolations, right? We know that the linear interpolation is always, in some sense, not outside the point set, meaning that the linear interpolation will always lie between P0 and P1 for u between 0 and 1. And every time the same thing will happen, and therefore the curve or the point on the curve will be inside the convex hull of these points. It cannot be outside, right? Because of the nature of the construction, which is a series of linear interpolations, right? Because each successive point can only be inside the convex hull of the previous set of points. So when I have these original set of points, then my new set points are these, and these. When I use these, the new set of points are this, which comes inside the curve. This also comes inside the convex hull. Likewise, the last point will always be inside the convex hull. And therefore, the convex hull property comes. For finding the point corresponding to u equal to 0, you know that you have to evaluate this at u equal to 0. And you know that in the first interpolation, I get this point. Second interpolation, I get this point. Third interpolation, I get this point. Then the first interpolation, I get this. And second interpolation, I get this. The third one, I get this. And therefore, it curve has to go through P0. And likewise, if you do the interpolation for u equals 1 here, you know that no matter what value of n is, it will always be P3 or Pn, as the case may be. Right? So the de Carlson scheme is now not only more intuitive and easier to understand and implement, but it also sort of provides you an explanation of why the Bezier curve has these properties that we claimed in the earlier slide. Right? That will always be inside the convex hull, and it will always interpolate the endpoints, and Okay. Quickly, the last property that I glossed over. I'll take the space here and tell you what that means. Remember, we said the property was that the curve can be transformed by transforming the control points. Okay. What does it mean? So to explain that, let me take a simpler example, right? Let's say that you're looking at a combination of points, which is a weighted combination, right? So each point has some weight. I multiply the point by the weight and add it up and take the sum, and that's the point that I get here on P. Now I add one condition that the sum of the weights is equal to 1. Okay. This is not unrealistic. In this case, this is an example of such a combination, right? That I have a point which is a weighted combination of these 2 points P0 and P1, but the weights are 1 minus u and u, and they add up to 1 always. Right? So that's an example of this kind of a combination. Now, the reason why this is significant is that supposing I do a transformation on the point, right? Now, a transformation can be written as a rotation, which multiplies the point, and a translation, right? T. So this is some vector, x0, y0, z0, and this is the 3x3 matrix, right? For a rotation about z-axis, if you go back to either graphics or robotics or any other course that you might have taken in the past, you will see that the term looks like this, cos theta. I think there's a minus somewhere. I'm not sure where. And so this is a 3x3 matrix that sort of corresponds to a rotation about the z-axis by an angle theta, right? The reason I write this is just to tell you that any rotation is written and can be written in the form of a 3x3 matrix. Right? It can be about some arbitrary axis, then all the columns will be filled, or it can be about the y, x, or z axis, in which case those entries will be equal to 1. And that will be the case. Okay, let me just quickly show this and then we'll pick it up in the next class. So, and translation is basically just D1, D2, D3, you know, along the three axes. You just add it to the point and the point would have translated by that amount. So this, now if I do this here, it looks like this. Sorry. Not what I wanted. Okay, let me just go back and write it correctly. Right. So I replace P by alpha I pi and plus T. That's all I have done. Okay. Now I sort of do this, and in the next step, the significance of the weights adding up to 1 should become clear to you now. I can do that. And therefore, now I can write this as sigma alpha I r pi plus T. Okay. So I have just done one trick here. Otherwise, it's all algebra. The only trick here is that T can be written as T multiplied by 1, but 1 is also written as sigma alpha I because that is equal to 1. And therefore, you know, I get this reduction. But what does this reduction say? What this is saying is that I can transform the weighted combination, or I can transform each of the points that form the weighted combination and then take the weighted combination, and the effect is the same. Okay, that's all this says. Now, what it means to us in terms of the property that I had listed in the previous slide, we will pick it up in the next class and then continue from there. Okay, any quick questions right now? Otherwise, you know, I will recap this in the next class and you can ask me questions. I hope you'll have had time to go through all these and we can discuss that. Any quick questions? Okay, if there are no questions, then I will leave you. It is going to be 3 and I need to get into another call, but yeah. So let me just exit that sharing, stop sharing part, so that, yeah. Okay, then we'll see you on Monday morning or noon in the same class. Yes, please.
Thank you, sir.
Thank you. Yeah. Thanks to everyone. We'll see you next week. Yeah. Bye-bye.